In the last video, we had travelled down more than 20 kilometres from the surface of Kent, and we're still in the felsic crystalline basement of the continental crust. To see the next big transition, we need to zoom out a bit. In this next column, which extends 200 kilometres down from the surface, the sketch of our journey so far is almost too small to see. And we have twice as far to go, down to 40 kilometres, before we reach the base of the continental crust, known as the Moho. In Ohio, it is 40 kilometres down, but that depth is actually quite variable. In some places, it is more like 10 kilometres. In others, it is more like 80. Making the continental crust thicker or thinner is something that plate tectonics does, so we'll talk more about this in a couple of weeks. The Moho marks the beginning of the mantle, so we have a major change in the composition of the rocks. We move from something like a granite to a rock called peridotite, which is still a silicate, but one that contains more iron and magnesium, which makes it denser. We call this composition ultramafic. Now, one important thing to bear in mind as we continue travelling downwards is that as we do so, we are seeing large increases in temperature and pressure. The temperature increases because there's a lot of heat still trapped in the Earth, left over from its formation. The pressure increase is because there is the weight of ever more kilometres of rock piled above your head. At 50 to 100 kilometres down, it is already much warmer than at the surface, several hundred degrees Celsius. But this is still relatively cold, so the peridotite is still, well, rock-like. It is strong and rigid, just like the rocks of the crust above. Because of this shared mechanical behaviour, although we are in a different layer compositionally, the crust and uppermost mantle are often put together into a single layer known as the lithosphere. This part of the mantle is therefore known as the lithospheric mantle. But as we go deeper, the temperature continues to rise, and at about 150 kilometres down, the rocks become just too hot, and we pass through a mechanical boundary, the base of the lithosphere. The composition of the rocks remains the same, but everything above this is the plate in plate tectonics, the bit that moves sideways over the Earth's surface. The stuff below it, known as the asthenosphere, does its own thing. It is plastic. It can flow in response to applied forces. But, and this is a big but, it is still solid. It gets close to, but remains below its melting point at these depths. Let's just say that again. The mantle remains solid. It is not a boiling vat of magma. It only melts in particular circumstances. It's actually not hard to realise that this has to be true. See if you can think of any evidence that tells us this. Silly putty, as a material which is close to its melting point at room temperature, is a good analogue for how the mantle rocks behave in the asthenosphere. Basically, it depends. If you apply a force quickly, then the rocks will respond elastically. They bounce back into shape when the stress is removed. If the force is strong enough, they can even fracture. However, a weak force applied over a long time, such as gravity, over several hours in the case of this silly putty, and thermal buoyancy forces over tens of thousands or even millions of years in the case of mantle rocks in the asthenosphere, will generate very different results. This plastic behaviour, permanent deformation, is due to a process called creep. At 200 kilometres depth, we're only 3% of the distance to the centre of the Earth, but fortunately, the inner 97% doesn't have as many different layers, so we can zoom out a bit and consider the whole planet. Here, I'm probably making the rigid outer shell that is the lithosphere a bit thick, but at true scale, it would be a little hard to pick out. Analogies abound comparing it to the skin on an apple, or the shell of an egg. But we're in the warmer plastic asthenosphere. Because it can flow, it convects. Hot mantle rises from deeper in the planet, and cool stuff sinks. But it is still solid, and these motions are slow. We're talking centimetres of movement a year. There is a lot of mantle. By volume, it is 83% of the entire planet. Strictly speaking, there is a rather vaguely defined transition from the asthenosphere to what is imaginatively called the lower mantle. But we're going to breeze past that until we reach the next really major transition, which occurs when we've got not quite halfway to the centre of the planet, 2,900 kilometres down. The boundary between the mantle and the core is a big compositional boundary, with silicates giving way to iron, or more accurately, mostly iron, with a scattering of other elements, including nickel. But it is also a sharp mechanical boundary. At the immense temperatures and pressures we find at these depths, over 3,000 degrees Celsius and millions of pounds per square inch, silicates are solid, if plastic like silly putty, but iron is above its melting point. Finally, after almost 3,000 kilometres, we encounter something molten inside the Earth. Just not molten rock, molten iron. This molten iron is also flowing, but much, much faster than the mantle. We're talking kilometres rather than centimetres a year. The outer core is convecting vigorously and pumping heat into the lower mantle. But as this vigorously convecting fluid is also a metal, these giant planetary currents also generate the Earth's magnetic field. Your compass points north because of the flow of giant rivers of liquid iron, thousands of kilometres below your feet. Before we get to the centre of the Earth, there is one more mechanical transition. With just over 1,000 kilometres to go, the combined pressure of 5,000 kilometres of rock and metal forces iron to form a solid inner core, despite the temperatures reaching almost 5,000 degrees Celsius. So having journeyed from the crust to the core, it's time to keep on going, to get to the crust on the other side. The first bit of our journey will be very familiar. The journey from inner to outer core, and from core to lower mantle, and even through most of the mantle itself, will look just like the journey down from Kent, just in reverse. But when we get to the upper 200 kilometres, things start to get interesting, because the oceanic lithosphere is a little different from what you find underneath continents. For a start, it is thinner. The boundary between asthenosphere and lithosphere does not occur at 150 kilometres, but at a depth of more like 100 kilometres. Remember, this is a mechanical boundary entirely controlled by temperature, so the implication is that the mantle under the oceans is warmer than at the same depth under the continents. Why? You'll find out in a couple of weeks, but it is due to the very different hows and whens of the oceans and continents constructions. Not only is the whole plate thinner, but the crust that tops it is thinner as well. The moho in the oceans is only 7 kilometres below the surface of the Earth, thinner than even the thinnest continental crust. And the crust itself has a very different composition, still a silicate, but with a composition somewhere in between felsic continental crust and the ultramafic mantle. The most common example of a rock with this composition is basalt, such as you see forming on Hawaii and other volcanic islands. And the oceanic crust is much less variable than continental crust. Rather than being a mixture of all three rock types, igneous, sedimentary and metamorphic, it is composed almost entirely of igneous rock. Most of it is formed from intrusive blobs and sheets, formed as magma cooled and crystallized beneath the surface. Perhaps the uppermost kilometre or so is made of erupted lavas. And then, on top, there is usually a thin veneer of sediments, made of debris that settled out of the oceans above. Our journey is complete. Hopefully, this has given you a good starting point for learning about Earth structure. For now, the thing I want you to notice and ponder is how a lot of the variability in the Earth occurs in that thin, rigid outermost skin, the lithosphere. The lithosphere is where plate tectonics happens, and that is not a coincidence. The outer shell of our planet is a place where there is a lot going on, and that is going to be our focus for most of this course. Just don't forget entirely about the stuff beneath. It sometimes has its say in Earth history as well.